We will see another experiment, figure of merit of a galvanometer. We get figure of merit of a galvanometer in practicals, whereas we get current sensitivity in theory. So this is obtained in theory, and its unit is divisions per ampere. So figure of merit, its unit is ampere per division. Now, the unit of figure of merit can be easily remembered by using the formula that you know in that you are using in practicals. So the formula that you are using is here. It is here. Yeah, K is equal to. So figure of merit is calculated as K is equal to E by R plus Rg into theta. Theta is the deflection, and it is number of divisions deflection in the galvanometer. Remember, E is in volt, so this is resistance. So this is V by R by divisions. V by R is current. So current can be replaced as ampere per division. So what do you mean by this figure of merit then? If you want to, so make this as one division. So we will do it here only. So from the formula itself, we will get the unit. So if you want to make this one division, how much current is needed? That is figure of merit. So if you want to define it, you can define it like this. How much the current required to produce one division deflection, that is figure of merit. So ampere per division. If the deflection in the galvanometer has to be one division, then how much current is required? So current required for one division deflection or unit deflection. Current required for unit deflection is called figure of merit. That is figure of merit. What is current sensitivity? Here make A as 1 ampere. Then if you want to produce if you pass 1 ampere current through the galvanometer, how many divisions will it make, or how many divisions will the needle turn? That is current sensitivity. So the number of divisions made or deflected for 1 unit of current. Deflection for unit current is current sensitivity, and current required for one division deflection, unit deflection, is figure of merit. So from here only you can define it. Of course, Viva will be asked only in the practical, so you better know what is figure of merit of a galvanometer. It is the current required for unit deflection. How much current is needed to produce a deflection of one division in the galvanometer? That's what you are going to find. Of course, you have a circuit for it, and it's very easy actually. So you should connect a galvanometer with two resistance boxes. One resistance box along with battery, in series with battery, and a resistance box like this. And another resistance box comes directly in parallel with the galvanometer. This is S. So this is always in the range 0 to 500 ohms. This is a smaller resistance box. Whereas this one will be a larger resistance box, 0 to some 5000 ohm range. So this will be larger one which comes in series with the galvanometer and battery will be larger one. This will be a smaller one, 0 to 500 ohm only. Now, how to do this experiment? So there is a meaning in this experiment. If you understand the meaning, then it will be very easy. So circuit, first you connect the battery along with the resistance box. Resistance box 0 to 5000 ohm range. That means maximum range is maximum key is 5000 ohm. So you can check it here. This is 5000 ohm key here, and this is only 500 key here. That is 500. This is 5000. So that comes along with the galvanometer and the battery in series. So you can start it from here: galvanometer to resistance box to negative. No keys are connected here. And this comes in parallel with the galvanometer. So this is yes. Okay, I should have changed. Okay, I will change a color here. Yeah, this is yes, and this is R. This is 5000 ohm here. This is 500 ohm here. But remember, in both the galvanometer, resistance boxes, infinity key is unplugged. It is removed. Infinity key is removed. That means both are open. So when you open both the resistance boxes, they are showing very high resistances. So this is 0 to 500 range, but this is infinity, this is infinity. Both are open. The circuit is open. No current is passing through any of the component. This is open means, sorry, not galvanometer, resistance box is infinity. Yeah, this is infinity. That means this is open. This is also open. It's like open circuit, no current is passing. So here there is a hidden thing that is not mentioned in the circuit, but you are going to connect. I'll remove all unwanted things here. So you are going to connect a battery across this. You are going to connect a voltmeter across this V, and there is a digital voltmeter, and setting it to 2 volt. That is not mentioned in the circuit. That voltmeter is not shown in the circuit, but you are going to do it. So connect a 2 volt battery, connect a voltmeter across the battery and set the battery to 2 volt. Of course, it is not shown in this circuit also here. It is not shown, but it is shown here. You can see that here. So a voltmeter is connected across the battery. So you can see the negative and positive connected, and it is connected to this voltmeter. You have to set this battery so that this reads 2 volt. That is the initial setting. And when you are doing that, this is open, both are infinity. That means they are not allowing any current to pass through. So that is the first step that you are going to do. So select, construct the circuit, and then first one, R is equal to infinity, S is equal to infinity, set the voltmeter, set the battery till voltmeter shows 2 volt. Set E is equal to 2 volt. That means this battery should show with the voltmeter 2 volt. This should show 2 volt. That is the first setting. But in the circuit, you can't see that 2 volt here in that voltmeter. So that you have to do yourself. Okay. So that is the first step. What is the second step? Second step. Of course, now you can remove this voltmeter. There is no need of having voltmeter throughout the circuit. But once you connect it, let it be here. No problem. So suppose it shows 1.99 volt, 2.01 volt in between. Don't change it. Let it be at the initial stage what you have set it. Let it be at 2 volt only. Even if it changes by a little amount, don't worry about that. So once it is set, then it is permanently set. Okay. Now E is set to 2 volt. Then now, yes, let it be infinity only. That means this is open. This is infinity only. We are not going to change this. But now set R. What do you mean by set R? So R is how much now? Set R means, so you know that in R here, this is R because this is in parallel with the galvanometer. So this, one minute, I will change this color because it's not seen. Yeah. This is R, sorry, this is S, which is in parallel with the galvanometer. That is this. Now I can't show it here. Oh, so it is here. Okay. This is R. Now you have to set this. So S is infinity. Battery is set to 2 volt. This is over. And now this infinity plug you have to put it. But while putting the infinity plug, remove either here 2000, 2002 keys, or remove one 5000 key, any one key. Any one is okay. But without removing, don't plug this one. So remove this key and replace it here. So say I have removed 2000, 2000, 2000 plus 2000 ohm. So totally 4000 I have removed. And one of the keys I have plugged it to R. Then galvanometer starts showing the reading. Why? Because as soon as you, I have to change the color again, yes. As soon as you plug R with some resistances, say 4000 ohm, now it is not infinity. So now it is connected to the circuit with a high resistance, but current can flow. A small amount of current can flow in this path. But no current can flow in this path because this is open. This is still infinity. So we have kept S is equal to infinity. So now plug R with some resistance, unplug some resistance and plug the infinity. put the key in the infinity so that current flows through this. How much current? So that galvanometer deflection is 30 divisions. That is the condition. So R is equal to how much? So that deflection is 30 divisions. That is the next step. So first step, all infinity, circuit is open, R equal to infinity, S equal to infinity, set T equal to 2 volt. If it is already set, then you are happy. Second step, with E equal to 2 volt, S equal to infinity, set R. That means plugging infinity. So infinity has to be removed now. With R some 4,000, 5,000 ohm, how much resistance is required? And that will produce a deflection of 30 divisions. That is the second step. So now we have, say this is 4,000. Say 4,000 ohm. So now we have, so I will switch on to this circuit now. Or we will do it here. I'll rub the unwanted things. So this is unwanted, yes. So I will write again what I have done here. Yes. So I will change the color, right? Yeah. White color. Yes. So what did I do is, after setting this to 2 volt, this infinity is kept as it is. But here I have removed some 4,000 ohm and plugged this key. Infinity is plugged and I have removed 4,000 ohm. Say for 4,500 or 4,200, say 4,200 ohm. I have got deflection in the galvanometer as 30 here. This shows 30 deflection, say 30 division. That much is over. Now what is the third step? For third step, you have to introduce S now. Third step, we have E is equal to 2 volt, R is equal to 4,200 or 4,000 ohm, and galvanometer is showing 30 division deflection. And in all the previous cases, the galvanometer was showing 0 deflection. Now it is showing 30 division deflection. Now set S. Set S means you have to remove infinity now. In the sense, you have to put infinity, close the infinity key. So remove some 100 ohm or 150 or 120, put it to infinity. Put one of the key to infinity. So S is equal to maybe 100 or 120 ohm, so that deflection in the galvanometer falls to 30 division by 2, that is 15 divisions. It falls to half of the previous case. Sir, why does it fall to half of the previous divisions? We didn't change R. We have kept 4,200 only. And the division was 30. As soon as you change S from infinity to some of the resistance like 120 ohm or so, why this division has fallen to 30? Because now that current which was passing through this circuit and a portion of the current starts flowing to this circuit also. So what the current flowing through the first circuit has reduced now because we have switched on this one. So some current will flow through this. This current reduces, that reduces the deflection here. So if you want to reduce this deflection by half, that is 30 division by 2, that is 50 divisions, 50% of the current should flow through this. So when the 50% of the current flows through this, what is that resistance that you have to unplug, which is same as the resistance of the galvanometer? Of course, that theory I don't touch it into now. So find out that yes, which produces half deflection in the galvanometer. That is the next step. So record all those values here in the tabular column. So first they have here you see set E. Now when you set this one R equal to infinity, S equal to infinity, remember they were not unplugged. Only infinity was unplugged. Next, then with the E equal to 2 volt. So here all in these cases E is equal to 2 volt, that is not changed. Now when R is 3,100, the deflection in the galvanometer was 30. That is the two steps that we are doing. Next we go for R. So when this is 3,100, this is 30 divisions. When you remove 100 in RG, this will never be 30 divisions, it will be 15 divisions only. So number of divisions will reduce by half. But if you put this 100 back, again you will get 30 divisions back. That you have to take care of. Okay, so what you will do for the next reading? Next reading will be like this. Number of divisions will be different, that's all. See, second set. For the second set, you can do it like this. Again, Again, E need not be changed. So this is the second step. Say the number of divisions required is 28. If it is 28, E equal to 2 volt, already said. R is how much? That means this is how much. So that galvanometer deflection will reduce to 28, not 30 as earlier. So if you want to reduce the galvanometer deflection to 28, then R will be more than the previous value, because more current in this circuit means more deflection in the galvanometer. Lesser current in this circuit means lesser deflection in the galvanometer. So if you want to have lesser deflection, you should pass lesser current. Lesser current means more resistance you have to unplug. So more resistance, more than the previous value. If you have got 3000, then next case will be 3400 for 28 deflection. So find out what is that value of R, 3400, say. Then because earlier was 4000, here I have to take this value. If it is for this one, then 4000, then it is 4500. So that deflection is 28. That is the next step. What about the very next step after this? That is like this. For E equal to 2 volt, R is equal to 4500. Then if you want theta by 28 by 2, that is 14 divisions, how much S you have to unplug? That is the next one. So S will be same as before. It may be, if it is a 120 ohm earlier, then it will be 120 ohm here also, no change. There may be a small amount of change. Say it may be 110 ohm or 100 ohm, something like that. But it will be around that only. So here you have got, in all cases it is 100. But this 100 is for half of 28. This 100 is for half of 30. This 100 is for half of 26. So every time. Next trial, again, if you want to have 26 divisions, you have to remove R. And if you want to reduce it by half deflection, what is G needed? That is 100. So you'll keep on doing like this and then calculate K value for each trial. Remember, for all these trials, you have to calculate K every time by using this formula. But when you use this formula, you will get 10 to the power minus 5, remember, because denominator will be a larger value. In the numerator, you have only 2 volt. You take some values and calculate it once again, and you will check it. Okay, every trial you do it, please, because in the examination, otherwise you will find it difficult. So here you will get only 2 volt numerator, for example, E by R plus RG. R plus RG is this one, 3000. It will be 3200, 3100 plus R plus RG into theta divisions 30. So that's what you have to do. So that will be 2.08 into 10 to the power minus 5. So everywhere you will have 10 to the power minus 5. Meanwhile, you will also have 10 to the power minus 5. And unit is ampere per division. So how much current is required for one division deflection? That is figure of merit. Yes. Thank you.